So how we can solve it using iterative approach. Okay. So for the iterative approach, we will try to mimic the recursion thing, like how stack moves in recursion and how we jump from one node to another in recursion. That thing we will try to mimic from recursion. Okay, so in the recursion we use memory stack, stack memory, but here we create our own stack. Okay, so stack is of type tree node. Hmm, one second. Okay, okay, for the recursion, we want to store the answer. We create a result array list. Okay, so we start from root node. Okay, and our current pointer is at root firstly. Okay, so we start, and initially our stack has just root. Okay, and we will keep running loop until current is not equal to null or stack is not empty. Okay, so first thing, we let's say we are here, so we will just keep moving to the left until there is no node left. Okay, so let's do this thing. While current not equal to null, current equal to current dot left. Okay, and we can just add current here to our stack. Okay, so let's say this is our tree. First we add 1, then we go to 2, we add 2, then we go to 3. Okay, after sorry, not 3, 4 here. Okay, so after reaching here 4, mm, we move to left, but left becomes null here. Okay, so now we jump back to 4, and when we come back to 4, we know that its left side is already visited, right? So it means we can directly take our 4 as the in-order node. Okay, so here we take a node, front node, top from our stack, and we just add it to our result. Okay, after adding it to our result, we can go to right side. Okay, so current will be equal to top dot right. Okay, and similarly on the right side, it's null, but stack is still not empty. So we come here, current is not null. No, actually current is null. Okay, and we can add a condition if total right is not equal to null, we add this condition. But here total right. Okay, let's try to try and run this. Let's say we are at 1, then we go to 2. 1 second. We are at 1, then we go to 2, then we go to 4. 4 left is null. Okay, so current becomes null. Then we pop our stack and pop our 4. Then we add our 4 to our result. Then we top dot right not equal to null. No, top dot right is null. Okay, so we skip this one. We again run the loop because stack is not empty. Stack has 1 and 2. Current is null, but this one is true. Okay, so we continue with the loop. Current is not equal to null, but current is null. Okay, so we pop from our stack the top value, we add it to our result. Top dot right not equal to null. Yes, top dot right is not equal to null, so we point our current to top dot right. Okay, so our current is this. Okay, now we can just continue with the loop. Current is not equal to null. Yes, current is not equal to null, and stack is also not empty. Current not equal to null. Keep adding current to the stack and keep moving to the left side. Okay, so we add 5, then we go here, we add 6. So but its left is null. Its left is null. Okay, left is null. So loop is completed. Then we pop from our stack 6, add 6 to our result. 6 right is null, so we skip this one. We go here. Current is null, but stack is not yet empty. So current is null. Pop from our stack after 6. We can pop 5. So we pop 5 and add it to our result. Then 5's right is not equal to null. Yes. Move our current to top dot right. So here is our current. Okay. Now continue with the loop. Current is not equal to null. Yes, current is not equal to null. While current not equal to null, keep adding current to our stack. Okay, we just add 7. Now its left is finally null. So we skip this loop. Then we pull from our stack. We extract 7. We add 7. Then its right is null. So we just continue with the loop. Our current is null, but our stack is not yet empty. So this will not run. We pop from our stack 1, then we add it to our result. So you can see that till here our Inorder traversal is actually true. 4, then 2, then 6, then 5, then 7, and than 1. Same thing we can do with the right subtree. Let's just run this. Okay, for 1 we pop 1. Okay, then 1 is right is not equal to null. Yes, it's right not equal to null, so we just move our current to top dot right here. Then here you can see that our stack is empty, but our current is not yet empty. So these both conditions are actually needed. This condition is needed, and here you can see that after coming here, our stack becomes empty, right? When we move our pointer here, our stack is actually empty, right? Because 1 is also popped from our stack, and we came to 3. Here you can see that it's little bit different from actual recursion call. In the recursion, we remove 1 in the post order when we have finally visited all the nodes. Then it gets removed from the stack. But here we are removing it as soon as we know that मतलब हमें इससे कुछ काम नहीं है. So then we just remove it, right? So here it's 3. We remove 1 from our stack, then we move to 3. So current is not equal to null. Yes. So add current. Okay. So add 3 to our stack. Then it's left, but left is null. Okay. So we come here, pull from stack, and it to our result. It's right is not equal to null. Yes, right is not equal to null. So move to right. So we come here. Then current not equal to null. Yes, current not equal to null. But our stack is empty here. Okay. Okay. So add current to our result and move to left. So we add current to our stack and we move to left. Then we again add to our stack. Then its left is null. So we just come back, and here we pop from our stack. Okay, and add it to our result. Its right is null, so we go here. Then current is null. We again pop from our stack and add it to our result. Its right is also null, so the loop stops, and now you can see that current is also null and our stack is also empty. So here our loop will end and everything will stop. But in the recursion thing, everything stops after first. This will be added to our stack recursive call 2, 4, then 2 is removed, then 5 added. So at this point 2 is already in the recursion, it's not yet removed. But then 6, then 7, then 7 removed, then 5 removed, right? But here as soon as we go to 7, we from 6 we go to 5, we just removed because we know that we don't need it in the future. So we just remove, then we go to 7, then 2 and 1, 3 and this. Okay. So don't try to confuse it with the actual recursion call. It's way different from the recursion. Okay. We are using stack similar to recursion, but the way it runs is very different from recursion. Okay, okay. So see you in the next video where we will solve in order traversal using Morris traversal. Okay, so using Morris traversal, we can solve it using of one space. Here you can see that we are using stack as a space, and the maximum nodes which can get added to it are of n, right? Because here this much node of log n space we are using here. Okay, using Morris traversal, we can solve it using of one space complexity. Okay, so see you in the next video. Bye bye.